Here we want to look at the ratio test. Alright, so our PowerPoint slide said for series a sub n, suppose the sequence of ratios a sub n plus 1 divided by a sub m has a limit, and L is that limit. Then if L is less than 1, the series converges. If L is greater than 1, or if L is infinite, then we say that a sub n diverges. And if L equals 1, then the test fails to tell us anything about the convergence of the series. So if we look over here on our sketch pad, I have it sort of written out in my beautiful handwriting. So why do I say this is related to the geometric series? Well, what if we have the sum k equals 0 to infinity of, say, r to the k? Alright, well, what is this ratio? Well, the ratio between the n plus first term and the nth term is r sub n plus 1 divided by r sub n, which is just r. So I'm taking the limit as n goes to infinity of that, and I get just r. And so from what we saw in the convergence of the geometric series, if L is less than 1, r is less than 1, then it will converge. R is greater than 1, it will diverge. If it's equal to 1, well, it diverges here, but we can see that's not always the case. For instance, if we look at the sum k equals 0 to infinity of 1 over k, alright, then the ratio test gives us the limit as n goes to infinity of 1 over n plus 1 divided by 1 over n, which is the limit as n goes to infinity of n over n plus 1, which is 1. And this is the harmonic series, so we know that this series diverges. However, the test, of course, does not tell us that. We just know that. But if we look at the sum of 1 over k squared, okay, I'll skip some steps here. This is 1 over n plus 1 squared divided by 1 over n squared, which is n squared divided by n squared plus 2n plus 1, and that limit goes to 1. But this series, of course, converges. So the point of the test failing is we can have that this ratio goes to 1, and sometimes the series diverges, sometimes it converges. Here it diverges, here it diverges, here it converges. And any other p-series for a higher power will also have the ratio equal to 1, and those will all converge as well. So that is the ratio test. Now, the ratio test was first popularized by D'Alembert in 1761. It wasn't until later, until 1823, when the root test was first publicized by Cauchy. The root test is typically more difficult to deal with, but is actually a stronger test. In other words, it will show convergence or divergence of some series where the ratio test will fail. So what we do for the root test, okay, if we have a series, then we look at the limit as n goes to infinity of the nth root of a sub n. And we have the same sort of things. If this root is between 0 and 1, then the series converges. If it's bigger than 1, then the series diverges. And if it's equal to 1, then the test fails. Okay, so looking at this, alright, again with the geometric series, if we have the sum of r to the k, then I'm looking to the limit as n goes to infinity of the nth root of r to the n, and well, that is just r. And so again, if r is less than 1, the series converges. If it's greater than 1, it diverges. Otherwise, if it's equal to 1, well, for the geometric series, it still diverges. But we can see the test fails. If we want to look at other examples of that, or where this fails, all right, to show that the root test is stronger, okay, it's stronger than the ratio test. Well, let's look at the series. The sum n equals 1 to infinity of 2 to the negative 1 to the n minus n. So let's think about what this series is. If n equals 1, then this is 2 to the negative 1 to the first minus 1, plus when n is 2, 2 to the negative 1 squared minus 2 plus 2 to the negative 1 cubed minus 3 plus, and I keep on going. So see, negative 1 to the first is negative 1 minus 1 is 2 to the negative 2 plus negative 1 squared is 1 minus 2 is 2 to the negative 1 plus 2 to the negative 1 cubed is negative 1 minus 3. This is 2 to the negative 4. And it goes on. Next will be 2 to the negative 3. And 2 to the negative 6 plus 2 to the negative 5. And so it's sort of the geometric series, but with every other term switched. And so what would happen here? Well, if we look at the ratio test, all right, then I have what am I doing here? The limit as n goes to infinity of a sub n plus 1 divided by a sub n, and that is 2 to the negative 1 to the n plus 1 minus n plus 1 divided by 2 to the negative 1 to the n minus n. Alright, now what does that equal to? Well, I'm going to have two cases here. If n is even, then negative 1 to the n plus 1 is going to, see, n plus 1 is going to be odd, so negative 1 to the odd is negative 1. So I get 2 to the negative 1 minus n minus 1. And so I'll look at that again in a minute. And then if n is odd, excuse me, that's divided by, this is still n even, divided by, see, n's even, so this is 1 minus n. So here I have 1 minus n. That is all if n is even. And if n is odd, then I have 2 to the negative 1 minus n minus 1, because n plus 1 is now even. That's not negative 1, that's 1. Divided by n is odd, so now 2 to the negative 1 minus n. Now this one is 2 to the minus n over minus n minus 1, and so that is going to be equal to 2, because I have 1 over 2 to the minus 1 after I cancel out the negative ends. And up here, what am I going to have? Well, I have 2 to the negative 2 minus n over 2 to the 1 minus n. So the 2 to the minus n's will cancel out, and I end up with 1/8. So there is no limit here. This doesn't converge. It alternates. As n goes to infinity, this is either 1/8 or 2, the ratio. So the ratio test fails. Now if I look at the root test, okay, I take the limit as n goes to infinity, and instead of writing the nth root, I'm going to make it to the 1 over n power, so 2 to the negative 1 to the n minus n to the 1 over n, which is the limit as n goes to infinity of 2 to the, let's see, negative 1 to the n over n minus n over n, which is minus 1. Alright, as n goes to infinity, this is staying at 1 or negative 1, and this is going to infinity, so that's going to 0. So I get 0 minus 1, which is 2 to the minus 1, which is 1/2. So this limit is equal to 1/2, which means the series converges. And we see the series does converge because, I mean, in the infinite limit, this is essentially, I mean, every other term is the geometric series, and for the even sums, and the odd sums is just flipped by one term, and it's the smallest term. So it's going to converge to the same thing the geometric series does. So often, if we don't have a lot of powers in or all powers in our series, the root test is very difficult to compute, but there are times when it is actually a stronger test than the ratio test. So more often we want to use the ratio test, but sometimes we have to use the root test. So we've seen the root test and the ratio test, how they work, along with the integral test and the limit comparison test. For homework, work through and turn in series 1 through 7 on slide 61 of the class notes. You may also want to look at the convergence handout that is linked there. That is something that Dr. Baldry uses with his calculus classes, his Calc 2 classes, and kind of steps through his view of how you should look at what test to use when. So if you have any questions, feel free to email me about that, and have those by the next time we meet. And so I will have some more videos about power series and Taylor series sometime later this week.